Hi, my name is Camilo, and I'll be presenting modular memorability, tier representations for video memorability prediction. In this paper, we work on estimating video memorability, an intrinsic metric that estimates the probability that humans will remember a given video. This metric is consistent across populations, but highly unintuitive, which makes it a very interesting and challenging problem to solve. Our main contributions are first, an in-depth analysis of factors of video memorability, what contributes to it, and a classification into different tiers. We use then this information, this classification, and an additional measure of distinctiveness to build a novel model that beats the state of the art. And then we leverage the model structure to get insights on what contributes to memorability, and we perform an interpretability analysis. The main model that we introduce has a modular structure and generates embeddings for each one of the modules that are fused together to regress a memorability score. And the memorability scores that we predict are very accurate because we beat the state of the art on the two main data sets for memorability, Memento 10K and VideoMem. So what is memorability? Memorability is this intrinsic property as visual stimuli that makes it more or less likely to be remembered by humans. It's very consistent, but highly unintuitive. And more importantly, video memorability specifically is harder than images. There's a lot of additional factors like motion, surprisal emotions, and other things that make it very hard to predict. Memorability ground truth is usually obtained with a simple setup where 3-second videos are shown to participants one after the other in a 10-minute or more sequence. Some videos are repeated and participants are just asked to detect the repeats. When you do that and you aggregate across participants and weight the responses according to the time between the first and the second presentation, you can get scores that are very indicative of the probability of recall of these 3-second snippets. Existing work has attempted to predict video memorability, but they have several limitations. The first one is they don't draw inspiration from the brain and from likely pathway to memory. The second is that they don't take into account that videos that stand out tend to be memorable. There's no measure of distinctiveness. And the third is that they're usually black box models that lack interpretability. We attempt to remediate these factors. And the first thing that we do for this is to separate the factors that contribute to video memorability into different tiers. We instantiate 3 main tiers, a low-level, mid-level, and high-level tier, where we categorize different types of properties that tend to impact memorability. In the low-level tier, we have things like color, brightness, motion, contrast, and others. In mid-level, we look at object semantics, the background, the scene, the objects that appear, and their saliency. And in the high-level tier, we look mostly at action, emotions, surprisal, and other things. Finally, we instantiate this distinctiveness component that modulates memorability and controls the other factors. If something is distinctive, it tends to be more memorable. Our model separates between different tiers by design. So we instantiate a low-level raw perception module, a mid-level scene parsing module, and a high-level event understanding module. All of these generate embeddings that are fed into this contextual similarity module, a module that essentially measures how similar these embeddings are to the rest of the corpus, and generates an additional embedding that is then concatenated and fused to generate our memorability scores. The distinctiveness module is key to what we do. And the general idea, as we said, is that videos that stand out from a specific context tend to be more memorable. The way that we compute this is essentially by comparing features of the entire corpus to the features of a given video. And we measure distinctiveness in that feature space. There's many ways to do this, but our approach is to cluster the entire corpus using dbScan and then training a simple NLP classifier to predict the labels of those videos. We end up with a few clusters of videos that are quite meaningful and some that are significantly different from the rest of the corpus. Our training procedure requires the introduction of the Spearman run correlation metric. The Spearman run correlation is similar to Pearson correlation, but it doesn't care about linearity. It cares mostly about the ranking of the list of elements. This is really good in our case because we attempt to ensure that memorability only cares about ranking itself, and we make sure that it doesn't care about the differences in systematic differences in ranges of outputs of our model versus the ground truth. For the training procedure for Memento 10K, we use a loss that is essentially MSE with tail penalization, ensuring that assets in the tail or elements in the tail are not incorrectly predicted. We additionally have a loss on video mem, which is essentially a weighted mean between MSE and Spearman rank correlation. This and other training parameters allow us to get nice rank correlation curves and perform really well on mem10K and video mem, the two prime data sets for video memorability. Our model beats existing approaches as measured on Spearman rank correlation, which is typical for memorability. And most importantly, it keeps a degree of interpretability. So it's able to understand things like whether a certain component or a certain module in our setup draws memorability or tends to decrease memorability or increases memorability. In this case, for example, our model is saying that the components of the low-level module tend to bring memorability down, while the scene and the semantics of this video tend to be memorable. Here, it's different, where the motion appears to be memorable, but the event itself is something unmemorable and tends to bring the overall score down. Each module specifically learns representations that are meaningful and substantially different from each other. This is quite interesting to understand how these models are generating those features and clustering them in their high-dimensional spaces. We perform T-SNE visualizations to show that our low-level, high-level, and mid-level representations tend to be quite different from each other. Our model is particularly good for certain things like understanding specific action or objects that tend to be memorable and gathering peculiar semantic context and utilizing that for its predictions. It usually has trouble with videos that have strong variations, that have lots of blurriness or complex semantics. It overestimates memorability of scenes that are semantically bland to humans or that are very dynamic with no clear action. And it underestimates the memorability of scenes that tend to be emotionally salient or particularly bland, very related to outdoor scenes that have no specific semantic content to look into. So finally, to conclude, our contributions are an in-depth analysis of the factors of memorability, classification into tiers, a novel methodology for using that classification and a measure of distinctiveness to beat state-of-the-art, and finally, leveraging the model structure to get insights on its interpretability and understand what makes a video memorable. Our future directions are essentially understanding certain different parts of why the model fails. Specifically, in the case of complex semantics, our model tends to perform worse. If there are large variations in pixel intensity or lots of motion, it's hard for the model to make an accurate assessment. There's room for understanding how to research each model and make it better and improve its specific role. And there's space for overhauling the high-level module with the addition of emotion prediction, which wasn't done in this work. Thank you for listening. And for more information, please visit our GitHub and come to our poster. Thank you.